Our next speaker is Muhammed Uludağ from University, and he's going to talk about modular groups and its actions.
Thank you. So, let me recall my first lecture. It was already 4 days ago, so perhaps some of you have forgotten. So, first, so the aim of the first lecture was to say that in the end, the modular group ESL2Z is nothing but an encoding of the Euclidean algorithm. So I made some effort to make this a little more precise. I said that the Euclidean algorithm is nothing but the comparison process of two magnitudes. We are given two magnitudes and we are asked to compare them. And this gives automatically rise to the Euclidean algorithm. And if we want to encode this sort of algebraically, then we end up with the modular group. But there were two Euclidean algorithms. The original Euclidean algorithm gives rise to the monoid PQRS, which I call PGL2M, of matrices with non-negative entries of anti-terminal plus minus 1, PS minus QR plus minus 1, and entries are non-negative. So, as we saw in that lecture, this group is generated by two elements, T and U. Each verb in this group, in this monoid, can be written as T to the power n naught, U, n1, etc., which corresponds to the continued fraction n naught plus 1 over n naught plus nk. Of course, here for the moment I assume that the processes always ends. And what happens with the non-ending processes, I'm going to discuss it tomorrow. So the modular group is not precisely encoding this version of the algorithm, this continued fractions, but something which is closely related to it, just a small relative, a small variation. It encodes the comparison processes by excess. It's a small variation of the excuse me, all of minus sinus here. And here, usually if you apply the comparison process to two magnitudes, then we see that these must be always greater than or equal to 2. And I said that if I remove this restriction, if I put 1 instead of 2 here, then I obtain the modular group. So PSL to Z, P to RS, PS QR equals 1, and entries RS are from Z. So the point is that elements of this can be written as words S T to the power M1 S, so on, where I mean T denotes the operator acting on the magnitudes, sending R to R plus 1, U sending R to 1 over R, and S sending R to minus 1 over R. So, but then you must ask, so these words with all nk are greater than or equal to 2, they correspond to comparison processes, so numbers, sort of rational numbers. I must gain something because I relax this restriction. Now I allow them to be 1. Okay, they cannot still be negative, but I allow them to be 1. What did I gain? Now this, if I consider all this process, all these words, then I will have represented negative rational numbers also. So I can say that PSR to Z encodes all comparison processes of positive or negative numbers, real numbers, rational numbers. Voila. But at this point I must make a confession. I said that the operators T, U, etc., they act on magnitudes. But I didn't define what magnitude is, okay? So my aim until this point was purely expository. I just wanted to say this word. PSL2 is nothing more than encoding of the Euclidean algorithm. Now that I said that, I can go on. But before that, I'm going to give you which magnitudes, to which magnitudes well, okay, for example, if you have two sticks, that is, if you have two lengths, then you can do this. If you have two piles of grain, okay, piles of grain, little seeds of grain, then you can apply these processes also, and the process always ends. You can be sure about it. But if you have your magnitudes are of this kind, if your first magnitude is A, and if your second magnitude is this, then evidently these are also magnitudes, right? These are also magnitudes, but you cannot apply the process to these magnitudes.
Is the length we should look, or the area?
Whatever, but area is better. Area is better.
Area is better.
Okay, why? Because those magnitudes from the very start, they must satisfy some axioms, okay? And Greeks, they did that too. I mean, what's the magnitude, or, well, given two magnitudes, I must be able to compare them, first of all. Which one is bigger? Here I cannot say it. And here, for example, I can say it. I can estimate it. Probably this is greater than this, I can say that. But then, to apply the process, I must be able to go on and subtract one magnitude from the other, right? And so on. So those magnitudes must satisfy these axioms. But you may, if you have lots of time, and if you are curious, you may try to adapt the algorithm to rectangular regions. Let's say you have A, and let's say that you have B. Now these two magnitudes are not comparable neither, but you can do something to make it, to adapt the Euclidean algorithm, and it will give you something very interesting and original. I mean, I haven't seen this anywhere. So the question is, big exercise is to how to adapt the Euclidean algorithm . Okay, so much for the first lecture. Okay, I want to say a few words about my next lecture. You may of course ask what about infinite works, infinite processes, non-ending, which correspond to non-commensurable magnitudes. In that case, let's say that I have an infinite process, n1 plus and so on. So these are same as infinite words on infinite words in the first monoid that I defined. So of type Tn0 u, Tn of u going forever. And in this case, you can show that if you cut this from till here, cut this till nk, and if you take a limit k as tends to infinity, where all n k's are greater than 1, then this limit always exists and represents uniquely a real number. This will be the content of my next talk, but I hope in a seamless way. Okay. Well, what about this lecture? This lecture, I want to say. So, okay, the lesson of the next lecture will be a real number is nothing but an infinite word in the modular group. So you see, I'm obsessed with the modular group. I have to explain everything with reference to the modular group. So the content of this talk is the following: a triangulation of a Riemann surface, or topological surface, orientable surface is nothing but a subgroup of the modular group. So I must define this statement in several ways. You can try to memorize it this way, but here I have to say combinatorial type and combinatorial and ideal triangulation. So I have some compact surface, and I have some compact surface with punctures, and I consider its ideal triangulations up to diffeomorphisms of the surface, underlying surface. They are called triangulation, combinatorial types of triangulations. So a combinatorial type of an ideal triangulation of a surface is nothing but a subgroup. Now I have to define this statement as well and say that conjugates class. Now I want to make this. So at this step I will need some facts. Some of them are hard, some of them are easy, but I don't have much time to prove any of those. So, am I on the right page? So first of all, it is not very hard. You can do it in a purely algebraic way without using any action on the tree or whatever. That the group PSR2Z is isomorphic to a free product. As I said, I mean, if you ever encountered Serre's books on trees and stuff, then you may be obsessed. You may end up with the idea that in order to prove that this is isomorphic to this free product, that the group must act on some tree. I must first find an action of the group on some tree, and then I'll be able to prove it. No, you can prove it in a pure algebraic way, and it is pretty easy. So this is the first step, and then from this action, from this identification, you can show that it acts PSR2Z acts on metric. And I'll do this. From this identification, I'm going to construct a tree on which this group acts. In fact, Ayberk did this in his first lecture. So this subgroup is the subgroup generated by S, and this is the subgroup generated by L, where L is defined to be T times S, is in my last lecture. So this is the transformation which stands 1 to 1 minus 1 over X. And S is just 1 minus 1 over X. Okay. And now you can show that any subgroup of the modular group is isomorphic to a copy of a free product of Z's, Z2's, and Z. For example, Z, free product Z, which is the free product on the two generators, is a subgroup of the modular group, and in many ways. Okay? Not in a unique way, in several ways. So the same free group may appear in several various ways as a subgroup. So this is the third interesting fact that you may want to know. Fourth, and this also Ayberk probably discussed to some length. The trace of M is a well-defined class, absolute trace, class function on PSR2Z. Class functions means that it is invariant under conjugations. And M is of order 2 if and only if trace is 0. In this case, and in the case that 1 equals 3, it is called elliptic. So if and only trace of M is 1. And elements of this is sorry, the 5. Elements of if trace M is 2, then M is called elliptic. Or excuse me, parabolic. In this case, M is of infinite order. And any parabolic M, any such element is conjugate to some power of Tn, some power of. And perhaps here I must add, if M is of trace 2, then it is conjugate to S, and if it is of trace 3, then it is conjugate to L. And finally, sixth important thing to know, that if the absolute trace is greater than 2, then we call M hyperbolic. And there are infinitely many conjugate classes, distinct conjugate classes of hyperbolic elements. in the modular group. And you may identify, you may put these into one-to-one correspondence with some several other combinatorial objects, such as Lindon work, Lindon works, or bracelets. Well, perhaps I can comment on this. I mean, it sounds complicated, but it's not so complicated because we know that the group is generated by these two elements only. So how a conjugacy class of an element can look like? So a hyperbolic element. So this will probably some hyperbolic element. Okay. If I conjugate this by S, then I kill the S in the start and I put an S in this side. So this is conjugate to this. Since all of these two elements are of finite order, then you see that, for example, if I conjugate this by L squared, then I'll have killed L here and put L squared here and so on. So there will be some finite word, and you will be, by applying conjugations, you will be just sliding this word to the right and to the left. And this determines the conjugacy class of the word. Okay? This is the conjugacy class of an element. There's a way to fix some piece of this in a canonical way, and this gives rise to the identification with the Lindon words or basics. In the same vein, in fact, you can identify these conjugacy classes by quadratic irrationals.
Okay, what's the word? It's a Lindon word FR. What's the last word?
Bracelets.
Oh, bracelet. Okay.
By the I made a small mistake. So if trace is C, then M is either conjugate to L or to its inverse. Okay, so if I have some time in the end, I'm going to talk about, and if you ask for it, I'm going to talk about some classical subgroups, congruence modular subgroups, and so on, which appears in number theory. But I'm not going to give Scalini's facts about